Okay, now it's time to talk about the second derivative, and then eventually we're going to get to the second derivative test. So we're talking about, well, what is the second derivative? In chapter 2, you pretty much were just finding the second derivative just as practice for finding derivatives. Like what it actually, and we had a moment where we talked about how its position, and the derivative position would be velocity, and the derivative velocity would be acceleration. But that's pretty much it. So now we're going to go a little bit deeper into the second derivative and say, what does this tell us about a function? Specifically, like if you know the original function, what does the second derivative tell you about the original function? Okay. So here we go. So the first thing, so as the function that looks at how f prime of x changes, so then the second derivative is indicating how is the slope changing. So not how is the y value changing, that's slope, but how is the slope changing? Like when the slope changes from one value to another, like every time slope has a number, so what is the, how quickly is the slope changing? Like is it going flat and then really quickly it starts going this way? Or does it go like slowly and gradually increase? What's happening with the change in the slope? That's what we're looking at. So first thing is you want to do, you're going to pause it in a second and you'll do this. Draw a function where the derivative is either positive and getting bigger. So the derivative is positive and growing also. Where the derivative is negative and decreasing, and the other ones. Again, each time you're drawing f of x, so you're drawing one where that function's derivative is positive for the first one, and that derivative is getting bigger all the time. All right, pause it right now and see if you can draw these things, just general functions. You don't have to do anything fancy. So we pause it. Okay, and here are my pictures, so like in the first one, it's positive, but it's getting bigger and bigger and bigger as you go, right? And the next one is negative, and it's decreasing, which means getting more negative. So, but on this third one, on this fourth one, sometimes people get confused about this. So it's negative and it's increasing. That means if it's already negative, it must be getting closer to zero. So it's flattening out. So this is actually, the function is decreasing, but the derivative is increasing on this one in the lower right. Okay, so that's the starting point. And so if f double prime of x is positive, so if the second derivative is positive, that's where the derivative is increasing. That's this one and this one. That's where the derivative was increasing. So please notice that it's stuff like this, right? It's either that kind of thing or this kind of thing if you put the two of them together. Right? And so this is described as concave up. Curving up, that's concave up, is the physical description of what that looks like. And if f double prime is negative, then you're on something like this. Like you could be on this part or you could be on this part, either one. And then, and that's called a concave down, of course. Yay, math made sense and labeled things correctly. Every once in a while you get a weird vocab word that's like, oh, why did they call it that? Okay. So definition, a point of inflection. So point of inflection is a point on the graph where the concavity changes. So it needs to be a point. It's called a point of inflection. So there has to be a point there. But not only that, it has to be the concavity changes. So it goes from concave up to concave down. So curving up, increasing slope to a decreasing slope afterwards. That would be an example of a point of inflection right where my fingers are. Or I could do it like this. Maybe I'll do it like that. A little bit easier. Old man, and all that. Right? You can see it's concave up before and it's concave down afterwards, after that point in the middle. So, you can have all kinds of graphs like that. You might go, I've seen that point, like I know what kind of graph that is, so try to be, but it doesn't have to have a derivative of zero like that. It could have it could be going up and then there's a moment where it starts going down. And there's a point in between where it switches from concave up to concave down. That would be a point of inflection. Yeah. So to show a point of inflection, like what you need to do is, and this actually I should say to find and to show a point of inflection is first, find when f double prime of x is equal to 0. because that's going to be the boundary points. Technically, it could be undefined, but only at an actual point on the graph. So it's possible that there's a sudden switch of concavity where it kind of jumps from a negative to a positive, but it would still have to be a connected graph. There'd still have to be a point there and stuff. So that's kind of unusual. Usually it's when it's equal to 0. And the second one is show f double prime of x changes signs. So it's not enough to show that it's not enough to show that the derivative is 0, second derivative is 0. You also have to show that it's actually changing signs. Very similar to our first derivative test earlier. Remember that? Where we had to show changing signs? Here, we'll give you an example. So here's one. So the first part of it is a review question. I thought, review question. Find the critical numbers, determine the nature of the extrema with the first derivative test. That's total review. And then part B, find the second derivative, analyze the sign graph of it to determine concavity and find any points of inflection. Okay, pause it and give these things a try. And after you've given it a try and you've at least find the derivatives, then I'll show you the answers. Okay, here are the answers. I only showed the local min. At x equals 2, you'd have local max. Yeah, but I didn't write all that out. It's usual, because at x equals 0, f prime changes, blah, blah, blah. Second one, second derivative, solved it, got x equals 1. And because at x equals 1, the second derivative changes, positive, negative, you could just say changes signs based on that. I think you get away with that. I'm not a BC grader, so I think you'd be okay. Let's just say changes positive and negative, keep it safe. Then it's a point of inflection. Now keep in mind, it said find any points of inflection, find a point. It didn't say find the x values of the points of inflection. It said find the points of inflection. You're like, what difference does that make? A point has an x and a y. So I had to find the y coordinate. So plug 1 back into the original function to find the y value, right? Because that gives you y values. First derivative gives you slope. Second derivative gives you concavity, the concave nature of the graph. And so I had to plug 1 back in, got the y value, and so 1, -3 is a point of inflection. Okay? Actually, yeah, we could do this. I was thinking about stopping, but I think we'll finish it and the video won't be too long. So imagine a function has a local maximum at x equals c. So it looks like this, and it's twice differentiable there. So you don't have to worry about second derivatives not existing or something. What would you know about the second derivative at x equals c? Think what this looks like. And so a lot of people look at that and they go, well, that looks like the second derivative, at something like this, a local maximum at c. Then f double prime of x would have to be less than 0. It'd have to be negative. And that's the idea of the second derivative test, but there's a catch. Watch it right here. So second derivative test. So another way to determine whether a critical point is a maximum or minimum. Remember first derivative test? I've got a critical number. Is it a min? Is it a max? Is it a neither? What does it tell me? And so the second derivative test is just another way of finding this. So given a critical number, so I've got a critical number, it's twice differentiable. I can find the second derivative. Then what if the second derivative is less than 0? Well, if the second derivative is less than 0 and it's a critical number, then x equals c. Actually, that should be f double prime of c, I guess, technically there. X equals c is a local, okay, the second derivative is negative, so it looks like that. It's a local max. Little confusing because it's negative. The second derivative is negative, and that makes it a maximum. You know how those two ideas kind of work backwards, like negative and maximizing. That seems a little weird, so watch out for that, like brain spasm that you can have over that. And then x equals c. If the second derivative is positive, then that's a minimum. X equals c is a local min. And if the second derivative is equal to 0, then this is no information. The second derivative test is useless and doesn't tell you anything. Bad news. It doesn't tell you that you have a neither. It tells you no information and you don't know anything about it. And you'd have to find some other way of determining this. Why? Well, I can name 3 functions that all have a second derivative, that all have a second, they have a second derivative that's positive, that's negative, they have a second derivative of 0 for all 3 of them at a specific point, and one's a max, one's a min, one's a neither. You want the examples? Y equals x cubed, y equals x to the fourth, y equals negative x to the fourth. At all of these, at 0, the second derivative is 0. So you would say, oh, the second derivative is 0, and you might say it's a neither, but we know what these look like. You know, the cubic, yeah, that is a neither, but x to the fourth looks like this, and negative x to the fourth, these are my fast graphs, looks like this. Second derivative is 0 at 0 for all three of these functions, so all of them fall under this category. One's a neither, one's a max, one's a min. Useless. So just telling you, oh, the second derivative is 0, it's like, that's not informative. It just doesn't help you know anything, and you have to go, shoot, gotta do it somewhere, some other way. Yeah? And so for the last example here, use the second derivative test to determine the nature of the critical values on this one. So remember, this is the one we did before. 0 is a min and 2 is a max. And now we're saying, well, how would we do the second derivative test on that? So the critical numbers were x equals 0 and x equals 2. And just to write down, f prime of x was negative 3x squared plus 6x. That's how we found those. And f double prime of x, this is all just copying from the earlier page, is negative 6x plus 6. So to do the second derivative test, you say, well, what's the second derivative at 0? I know it's a critical number, and so what's the value of that? F double prime of 0 is 6, which is greater than 0. Therefore, x equals 0. At x equals 0, it's, or I'll say f of x has a local, the second derivative is positive. So if the second derivative is positive, we're like this. So therefore, it's a local min. And f double prime of 2 is negative 6, which is less than 0. And so at x equals 2, f of x has a local max. Please notice, I only found the min earlier, but please notice this backs up what the first derivative test said. You'll never do both, I mean, unless the teacher's being, kind of a pain in the butt. You never have to do both. You can just do one of them. Either one of them, depending on the situation, might be easier. Sometimes maybe the sign graph would be hard to analyze, or sometimes maybe find the second derivative would be really hard. And so in either case, you could do the other option, and that might be easier. Okay? Yep, I'll stop there. And so that's the second derivative test. Take a critical number, take that x value, plug it into the second derivative. So it's wild. It uses all three. Where we want to know on f of x, where does it have a max or a min? So we find the first derivative. That gives us our critical numbers. Now we need to find out, well, are those critical numbers representing maximums or minimums? You can do it with the first derivative test, but if you choose to do the second derivative test, you look at the second derivative and say, well, is that positive or negative? That tells me what's happening on the original function in terms of its concavity, and so then I can possibly find out if those critical numbers are maximums or mins on the original function. Whoa, that was intense. Okay, hope that helps and helps clarify or helps explain the second derivative test. And I'll let you know at this point, the next thing we're going to do is just kind of review what we've done, all the stuff from 3.1 to 3.4, because there's a ton of techniques, but that's coming next. That's it. Take care of yourselves and have a wonderful day.